Hi, today we are going to talk about acoustic in timber structures. But before starting, we need to understand the type of noise that is affecting our building, because the way of improve the acoustic performance of our building depends on the type of noise that we would like to improve. It's different if you're talking about an impact noise, so a noise produced by an impact, so for example people walking or when we move a chairs or this kind of noise. This is a noise that affects slabs and that needs mainly resilient material. On the other side we have airborne noise. This is a noise that affects both walls and floors, and it's produced by sounds that are propagated through the air. So for example, people talking, listening music, and this kind of noise. The structural noise is something in between impact noise and airborne noise, because when we produce one of this kind of noise, this noise can also propagate through the structures. Of course, in this case, we need to work at the level of the structures. And the problem of this is that it's very difficult to do that in a second moment. So, of course, because structures is inside the building, and it's very difficult to work on that in the future, so when the building is already constructed. And the third point is acoustic and ceiling. We will see the importance of air-tightness and the ceiling of the building. But just trying to go step by step and try to understand how to approach the acoustic design of a building. It's a general recommendation. We will see mainly example of timber structures, but it can be valid for also different type of structures. Of course, for have a successful project of a building, we need to consider acoustic from the beginning, because as I said, some solutions are difficult to be implemented in a second moment. For example, when we work at the level of the structure, it's very important to forecast this kind of solution at the beginning when we are designing the structures, of course. And also other solution needs to be designed in a first step, because for example we will have for floors we cannot improve that too much if we have limitation in the height of the floors, for example, or this kind of stuff. We need to work at three levels. First of all, we need to work on direct transmission of the sounds. A second level is the reduction of the flanking transmission. We will understand what it does mean. And at the end, of course, we need to pay a lot of attention to the details. But just we will see that step by step. First, we need to design our building starting from a solution that consider the direct transmission. What does it mean? That when we design a wall or a floor, we need to choose a solution that have a proper acoustic solution. In our catalog, you can find different solutions already measured in the laboratory or in construction sites that allowed you to understand the performance that can you expect in your building. So depending on the type of building that you are constructing. So if you are doing a CLT walls or a timber frame walls, for example, or if you are designing a facade, and depending on the solution and the layers that you are using, you can get a different acoustic performance. But starting from a solution, there is the possibility to improve the acoustic performance of your wall. Here are some examples that can help you to understand how to approach from an acoustic point of view a partition that need to be improved. First example are related to solutions that need to be improved and you don't have so many space to do the improvement. So these are thin acoustic uprates. First solution is to add mass to your wall. In this case, you can use our product like Silent Wall Bitumen or Silent Wall Bitumen SE and apply that to a plasterboard panel. So adding a plasterboard panels and a massive membrane allowed you to improve the acoustic performance of your wall. Another possibility is, instead of adding mass, adding a resilient material that separates the layers. So in this case, for example, you can see a solution in which we have added resilient material like our Silent Floor Pour or Isla Silent Floor text to a plasterboard panels. What happened in this case that the plasterboard panels vibrates, but the vibration does not cannot propagate to the timber, to the structure, because we have a resilient material that dissipates this vibration, and therefore the propagation of the sound. Another possibility is to have both kind of improvement. So having a massive membrane that allowed you to improve the airborne sound, and a resilient material like Piano A or others products in stripes, like for example our Silent Floor Pour. And this kind of product, so you have the both benefits. So from one side you have the plasterboard with the massive membrane, so for example our Silent Wall Bitumen SA, and this will add mass, and this will improve especially at low frequencies. And then you have a resilient interlayer that separates the plasterboard to the structure, so reduce the propagation of vibration to the structure, and also so therefore it improves the acoustic performance of the partition. Of course, this allowed us to have an improvement that you have read maybe around 8-7 dB up to 13 dB, sorry, in this case. So if you do the improvement on both sides of the wall, if you can do that. If you need to have a higher improvement, of course, it's not possible to work with this thin solution, and you need to work with supporting walls, which this needs more space but have a higher acoustic performance and allowed you to have an higher improvement. So there are two possibilities to construct there. One is to construct with structure made of timber. So and you can separate the timber studs with resilient material like Piano A, Silent Underfloor or other products, and add to the plasterboard panels always massive membrane like Silent Wall Bitumen SA or Silent Wall Bitumen. The best solution for having a higher acoustic improvement, but this needs more space, is to have self-supporting structure, which is completely separated from the original structure. Of course, this is the best solution because this allowed you to have a structure that is completely separated. So, of course, the vibration reached the first plasterboard, and this vibration cannot reach, or few vibration reach our separating wall, because we have an air gap and there are no direct contact between the first structure that we have constructed and the original structure. And as you can see, this improvement can be up to 8 dB if you are working just on one side, or 29 dB if you are working on both sides. Pay attention that all these solutions are cannot be double. So if you look into the solution that you that have proposed, if you are working just on one side, you can see improvement, for example, of 18 dB. But if you work on the both sides, the improvement is not the double, is less than the double. And this is due to the fact that acoustic performance works in logarithmic scales, and unfortunately, logarithmic scales work like that. So we cannot simply sum the benefits, and this is what happened. But anyway, we have seen that we can improve the acoustic performance of our walls, adding massive membranes or separating layers. But pay attention, because if we are working on a facade, many times the problem is not the facade itself, but it's the window, or if you have some ventilation elements or so on. So pay attention, because you need to understand where is the problem and work on the problem that you have. In this case, for example, if you have a window, the first things to understand the first things to understand is the window the problem, and eventually change the window, or at least improve the ceiling of the window. We will discuss better about that later, but you need to have wind tightness, so an external layer of wind tightness made with tapes, an intermediate layer for the acoustic insulation. It can be done with foams or cell expanding tapes, and you need to seal the window from the inside for the air-tightness layer using tapes or silicones or other kind of sealants. This was for walls. Now we can see what we can do for floors. Same as before, in our catalog, you can find different solutions in order to understand the performance that you can reach, depending on the layers that you are applying and the stratigraphy you can do. And starting from that, we can see some improvement. When we work for the improvement of floors, generally we cannot work on both sides. So, because generally the owner is just the owner of one floor, so or the topper one or the lower one. So, for example, if we can work only from above, what we can do is to construct suspended ceiling, or closing the if we have the beams, closing the beam with a plasterboard panels, coupling the plasterboard with a silent wall bitumen SA. And more than this, you can apply a separating layer, like for example piano A, or silent floor pour in stripes, or silent underfloor. And in this case, you can have both improvement, as we have said before. So we have we had mass, which can help from the acoustic point of view, and we have a separating layer that reduce the propagation of vibration through the structure. On the other side, if we can work only from above, one solution is to construct a screed and separate the screed with a proper underscreed. So a resilient membranes that reduce the propagation of vibration. We have done some measurements on CLT floor with this kind of improvement. From one side, we have constructed a screed, a dry screed made with dry panels. And And in another possibility is to construct a wet screed, so the most traditional solution. And in both cases, we can see that we can get an improvement around 21-22 dB of impact noise. Another possibility is to make a raised floor system with patterns and resilient layers, like for example piano A or silent floor PU in stripes. And this allowed us to get very good performance, an improvement of the impact sound of 31 dB. And it's allowed us also to have more space, for example, for installation. So in renovation, it can be also very useful for have more space for the entire renovation, not just the acoustic renovation. Of course, the best way to improve a floor is to have a full retrofit, so working from below, but also from the top. So adding suspending ceiling and also a raised floor or a screed more resilient membranes. To have a perfect solution, we can also add to our floor assembly resilient membrane under the flooring, like silent step or silent step alu, that allowed us to have a first separation and so a first reduction of vibration from the finishing to the other part of the flooring. Of course, these are suggested solutions that allowed you to think how to work on the acoustic and how to get an improvement, but it cannot be considered a completely guide for the acoustic design of a partition. Of course, also if you are talking about renovation, of course, to work in a proper way in a renovation, the first way is to have a measurement. The second one is to, according to the measurement, understand the problem, so what we need to improve, and according to that, design the proper solution, install the solution that we designed, and at the end, remeasure this, the partition in order to understand if we get the improvement that we are expecting. Of course, this can be done by an acoustician, and of course, if we have specific requirement, our acoustician is needed. But if you remember what we have said before, the acoustic design cannot just start from with the direct transmission, so just choosing the proper solution, because the second step is to thinking about flanking sound transmission, or better, this should be the first one, but in concept we think that after. So what is flanking transmission? So when we do a measurement in the laboratory measurement is done in a way that what we are measuring is only the performance of the partition. So the performance, for example, of the separating wall, because the laboratory is done in a way in which the structure is not connected. But when we are inside the building, what happened that the separation wall is connected to the other wall of the building, and noise is basically a vibration. So what happened that when we produce a noise, the noise makes that the separation wall vibrates, and due to the vibration of the separation wall, we can hear the sound on the other side. But what happened that in the building, in a common building, when we produce a noise, not only the separation walls start vibrating, but also all the walls and the floors are vibrating. So what happened, and you can see that with these arrows, that if you a side wall is vibrating, the vibration of these side walls will propagate to the other side walls on the other side of the separating wall, and this vibration will enter in the receiving room. So we will not hear only the sound produced directly by the vibration of the separating wall, but also produced by the side wall that is vibrating due to the contact with the wall, which is in the other room. Other component that cause the propagation of vibration is that the side wall is in contact with the separating wall, which vibrates more due to the fact that the separating wall is vibrating due to the direct transmission, so to the direct noise, but also due to the fact that the separating wall in contact with the separating wall vibrates, so receive this vibration and separate more. There is also a third path, which is when the separating wall vibrates, transmits their vibration to the side wall in the receiving room, and so the side wall in the receiving room are vibrating more. So what happened in the end? That in the laboratory we are just measuring the performance of the separating wall, because the laboratory is done in a way that what we can measure is just this part. But in the reality, what happened is that every side wall has three paths of indirect transmission of the sounds. And considering that we have at least 4 sides, like in the pictures, what happened that at the end we have 12 paths of transmission, of indirect transmission. And all this phenomenon is called flanking transmission. It's an indirect phenomenon that needs to be forecast before in the design phase, because of course it's very difficult to work on that in a second moment. So what we can do to avoid or reduce this phenomenon of the flanking transmission, so all this indirect propagation of the noise, the solution is to use resilient interlayers. So what is the idea? That if we have a resilient interlayer, the contact between the walls is not so high, and therefore when, for example, a side wall vibrates, the resilient interlayer reduces the propagation of vibration to the separating wall or to the other side walls, and therefore we have a reduction of this flanking transmission. So where we need to put the resilient interlayer? The resilient interlayer needs to be put between floor and walls, and they need to be installed in all the interface. So it's not enough to put the resilient interlayer just on one side, for example, only between the floor and the bottom side of the wall, but we need to put them also between the floor and the top part of the wall. Only in this way we can reduce all the flanking path. Resilient interlayers depends on the loads, and this is due to the fact that they works like a spring. And if we think how a spring works, we can understand then, depending on the load that we are applying or a spring, it can be more compressed or less compressed. Of course, the idea is that the spring have the right load applied on that in order to work in the proper way. It works like more or less a shock absorber of a car. And of course, a shock absorber works good if it's proper load. What is the load that needs to be applied? So which is the profile that we need to choose? It's the load that we have in the in normal life, of course. It cannot be the load that we are using from a static point of view, because if we are thinking about the static point of view, the load is overestimated for safety reason. But no one wants to have a good acoustic performance in a very hypothetical situation. We would like to have the acoustic performance in the reality. So we need to calculate the load in the proper way. And this is why when you look into the table of use of the products, you will see that there is a acoustic optimization, so a load gap that is recommended from an acoustic point of view. And this kind of load needs to be calculated considering the load applied on the resilient interlayer, which is done by the weight of the structure without any coefficient and just half of the live load. So the dead load without any coefficient and an half of the live load. And it is quite a reasonable way to calculate the weight and to have a good estimation of the load that are applied in the building. For the reduction of flanks in sound transmission, as I said, we can use resilient interlayers. We have two kinds of product. One is in EPDM and one is in polyurethane. Polyurethane is considered more durable, better performing at long term, and the way that we can estimate the performance of this resilient interlayer is we have two possibilities. One is using the estimation of the KIJ, so the estimation of the contribution of the resilient interlayer itself. In this case, we have done many measurements in which we have tested different kind of configuration, different type of fastening system, and this allowed us to provide a value that allowed us to estimate the improvement due to the use of this type. We have done also an European technical assessment, so an ETA on this product in order to have a certificate and value that are recognized by the third part and the external laboratory. We have done also the measurement with different loads because, as I said, it's important to use the different resilient interlayer depending on the load applied. And what we have done is to test the material with different load in order to guarantee that the profiles works depending on the load that are applied. Another possibility that is to consider the entire flanking transmission. So not only the benefit of the resilient interlayer, but to have the entire performance of the flanking transmission. We have done this using a special laboratory in which was possible to lift the upper floor and the upper wall and the floor, and to install in between walls and slab the resilient interlayer. This allowed us to measure the flanking transmission with and without our resilient interlayer and to provide the improvement of the resilient interlayer. So depending on the calculation that you are doing and the information that you have, you can use only KIJ, which is the performance of the resilient interlayer and of the joint, or to consider the RDF more FF, which is the combination of the entire flanking transmission. But important to know is that resilient interlayer are not just are inside the structure, so we cannot just consider the acoustic performance that are quite high, but we need to consider that the material needs to be designed to be inside the structures. This is why with Rothoblaas we have done many static tests in order to understand what happened to the fastening system if we have a resilient interlayer between the joints. And also we can provide the compressive stress at 3 millimeters, so to have the value, the performance of the resilient interlayer at the ultimate states. This is the value that need to be used by the designers of the structures. So this is the value for a static point of view, which is very, very different, as you can see, compared to the acoustic load that need to be applied, because this is, of course, with safety coefficient and so on. If we are talking about timber, also it's very important fire performance, and this is why we have also tested our resilient interlayer, our xylophone, against tests. We have done different tests, only with the joints or inside an entire building, in order to understand what happened. Because of course, if we are inside a structure, the resilient interlayer cannot be the weak part, and this we can demonstrate that it behaves good enough. But let's came back to our acoustic design. So we have seen that, of course, first of all, we have a direct transmission of the sound. So we need to choose a separating element, so a floor or a wall that performs good. But this is not enough. We need to work on flanking transmission, because we have this phenomenon of indirect transmission of the sound, and we have seen that we need to use resilient interlayer to improve it. The third part is to pay attention to details, and it is very important. So it's more related to the construction phase. Generally, it's not so high designed, but in some cases it needs to be designed, or at least we need to follow the construction phase in order to guarantee that the construction phase is done in the proper way. An example to understand what does it mean. We have done some tests on a plasterboard separation wall, in which there was an air leakage, and what happened is this air leakage reduced the acoustic performance of the separation wall, and the performance of this wall was only 25 dB. But only sealing this air leakage, which was quite important, what happened that we get an improvement of 24 dB, because at the end we get 49 dB of acoustic performance. So the wall is the same. Nothing changed. The materials are the same. So in our project, we don't notice any difference, basically, because we have two plasterboard panels, insulation material in between, and other two plasterboard panels. What happened that on one side we have sealed the joint, in the other side we haven't. Just because of that, just because we have take care of the air-tightness, we can guarantee the acoustic performance and have 49 dB. If we don't care about acoustic performance, air-tightness, we can get 25 dB. And of course, this is very, very different, and this is just a matter of details. For this reason, it's very important to take care about air-tightness. When we have an air leakage, we have problem from a thermal point of view. We know that passive valve recommend that, but we have also acoustic problem. So because through an air leakage is not just air passing through, but also warm passing through that, noise passing through that, and so on. So sealing the elements and components is very important. We have already mentioned that it's very important to take care about the sealing of the window, and I recommend to apply the rules of the 3 levels of protection. So seal the window on the outside with tapes or some sealant, seal the window in the intermediate layer, so where we put the window in contact with the structure with self-expanded tapes or foams. And third level of protection, the air-tightness, so seal from the inside with tapes or proper sealants. Other details that need to be considered: installation. If we have some plumbing or something that is passing some elements of the installation that are inside the building, this can cause some problem from an acoustic point of view. And the solution of that is to create, for example, an element that isolates from an acoustic point of view from these elements. We can use also massive membranes like silent wall bitumen or silent wall bitumen SA that allowed us to have good airborne sound acoustic performance with not so much space. Other kind of installation that are quite problematic is, for example, if we have tubes and we need to separate them from the mechanical part. So, for example, here we have this tube, we have the mechanical connection, and we can use resilient material to separate this element, because so when the tubes vibrates, this vibration will not pass to the structure, and so this noise cannot be propagated to the structure. And we already have said that many times. So when we have some part of installation that affect the air-tightness, it's very important to restore the air-tightness, so with sealant or silicones, foams, and so on. Be attention that this material need to be tested and be approved from an acoustic point of view. So not all the foams are suitable for this purpose, not all the material are suitable for this purpose. So we are arriving to the end of our presentation, and I would like just to resume briefly what we have seen. So in order to have a good acoustic design of the building, we need, first of all, to choose materials and stratigraphy that are tested and that allowed us to reduce the direct transmission of the sounds. We have seen that there are many databases. Also, Rothoblaas has one that allowed you to understand the performance that we can expect in our buildings. Pay attention to the reduction of flanking transmission. We have seen that this is an indirect phenomenon that causes the propagation of vibration to the structure and can worsen a lot the final acoustic performance of our separating elements. And at the end, pay a lot of attention of details. We have seen that air-tightness and separating the components, it's very important to guarantee the acoustic performance of all the solution. This was everything from my side. I hope that it was interesting for you, and I would like to thank you for your attention.